The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, so today, we're going to go on to section 9.2. But before we do, I'm actually going to take us back to section 5.2 to review rules to do with properties of exponents. Okay, so let's take a look at some rules from section 9.2. Let's say we have x cubed times x to the fourth power. Okay, so we're multiplying two powers with the same base. The shortcut is that we add the exponents. So x cubed times x to the fourth is x to the seventh power, or y squared times y to the sixth power is y to the eighth power. In general, we say a to the m power times a to the n power equals a to the m plus n power. So again, if you are multiplying two powers with the same base, you add the exponents. Any questions about that? Okay, so that's one of the rules. Here's another rule. If you've got a power raised to a power, you multiply the exponents, or let's say y squared cubed would be y to the 2 times 3 or 6 power. So in general, we say a to the m power raised to the n power is a to the m times n power. So that's a second rule. Any questions about that rule? So you got to be careful you don't get those two mixed up. Okay, let's see here. Another rule. If we have a quotient where we're, wait, I don't want to do that yet. Okay, let's say we're dividing two powers with the same base, like x to the seventh divided by x to the third. That would be x to the top exponent minus bottom exponent, which is x to the fourth power. So multiplying two powers with the same base, we add the exponents. Dividing two powers with the same base, we subtract the exponents. And we subtract the bottom exponent from the top exponent, not the other way around. So in general, we have this rule that says a to the m over a to the n equals a to the m minus n. And that's all in the numerator. We don't typically write it over 1, but I just want to make sure that you know that is up top. It's not like 1 over all of that. Okay, so that's a third rule. Let's see, what else have we got? If we have something like this, a product raised to a power, we attach the outside exponent to each factor inside. Or we might say in general, a times b to the n is a to the n times b to the n. If we have a quotient, like, let's see, x over 7 raised to a power, we attach the exponent to both the numerator and the denominator. Let's see, 7 cubed is 343. So in general, a over b to the n equals a to the n over b to the n power. And again, these are all, let's see, section 5.2. What page is that? Actually, I want to refer to and make sure I didn't miss any. In the regular textbook, it's on page 364. I don't know if it's in your textbook or online at the same page, but 364 has all of these rules. Let's see, we've done that one, that one, that one, that one. Also, if you have something raised to the 0 power, that's equal to 1. If you have something raised to the 1 power, basically, if you don't put an exponent, that's implying that there is a 1 as an exponent. So for instance, x is equal to 1 times x to the 1 power all over 1. But we don't tend to put all that extra stuff there, but it is implied. Okay, so we've got these two ideas. And then we have this one. Something raised to a negative power is equal to 1 over that same base to a positive power. So in general, a to the negative n equals 1 over a to the n. Likewise, if we had 1 over, let's say, y to the negative 2 power, that would be y to the positive 2 power over 1, or y to the 2 power. So basically, if you have a power with a negative exponent, if it's in the numerator, you can move it downstairs and make it a positive exponent. If it's in the denominator, you can move it upstairs and make it a positive exponent. Okay. So
On that one, it doesn't matter if it's even or odd. It will still make it in.
Correct. Yeah. Doesn't. So right. Okay. Also, you can have something like this. Let's say you've got x to the negative 3 over y to the negative 2. That would be y squared over x cubed. So you'd switch both of them, because moving this upstairs makes it positive, moving this downstairs makes it positive. If you had something like this, let's say 3 over x to the negative 2 power, that would be x over 3 to the positive 2 power, because you take the reciprocal and change the sign of the exponent. Okay, now that was a very quick review of those rules, and as we go along, if you need me to remind you, I will. But we're going to be applying those today, because in section 9.2, we're going to be talking about radical exponents, meaning now the exponents could be a fraction. So instead of just having like positive exponents and negative exponents and 0 exponents, now we might have an exponent of 1/2 or negative 2/3 or something like that. So first of all, let's look at how this thing works. Let's say I have the cube root of x squared. Okay, so this is written in what we call radical notation, because it uses a radical. I'm going to convert this into exponential notation. This is x to the 2/3 power. Now, the power is on top, and the index telling us what root is on the bottom of the exponent. Think of like a root of a tree. The root is on the bottom, so the root is on the bottom of the exponent. Okay, so for instance, let's say I have the cube root of 8 squared. That is 8 to the 3/2 power. Again, the power is in the numerator, the index, the root is in the denominator of the exponent. All right. Now, we can put both of these things into our calculator to get an answer. So let's start with this one. We talked yesterday about there was a button that was the xth root. So what we're going to do with our calculator on and cleared, we're going to put in the number 3. Then we're going to go second xth root. And then we're going to put in, I'm going to put parentheses 8 squared, close parentheses, equals, and I get 4. So I'm taking the cube root of 8 squared. You look confused, Lindsay. What's going on?
So your example, the 8 3/2, isn't that backwards? Shouldn't it be 8 2/3?
No, no. Oh, oh, yes, absolutely. You are so correct. I am so wrong. Thank
No,
you
why
so
can't I
much.
do that on my tests?
What's that?
So no, why can't I do that on my tests?
I'm just having a bad year, apparently. There we go, to the 2/3 power. Thank you. And I was just so sure that I was right and you were wrong. I guess I'm eating humble pie now. I will be the first to admit it when I mess up. Focus, focus. All right, let's see. Yes, now keep in mind, it's not 8 times 2/3, it's 8 to the 2/3 power. How do we put this in our calculator? We put in an 8, we use the little caret key. This next step is very critical. You've got to put parentheses around the fraction exponent, because if you put this into your calculator, it thinks you mean 8 squared divided by 3. So you have to tell the calculator that the 2 divided by 3, that whole thing is the exponent, okay? So if you put in 8 raised to the parentheses 2 divided by 3 power, you should also get 4, provided you write it correctly, unlike I did earlier, okay? So again, the exponent, the power is on top, the index, the root is on the bottom of the exponent, okay? Now, let's go back and let's look at this same problem again. The cube root of 8 squared. As long as both the cube root and the square are real, so in other words, as long as we're not taking an even root of a negative number, we could write that this way. We could also write it this way, meaning we could write it this way, and we could also write it this way. What am I doing here? Well, keep in mind, I often ask myself that. What am I doing here? So here, 2 times a third is 2/3. A third times 2 is 2/3. So we're breaking that fraction apart. We're kind of going backwards from what we normally do. But the reason for that is this. I could do the exponent first and then the root, or I could do the root first and then the exponent. Which is easier, to take 8 and square it and make it huge and then take the cube root to make it smaller, or to take the cube root and make it smaller and then raise it to a power? Generally speaking, this is going to be easier, to take the root first. You should get the same result, but you have a choice as long as they both are real. Okay. So having said all of that, give me just a second here, make sure I didn't miss something I was going to tell you. No, covered that. All right. So what we're going to do now is just evaluate some exponential expressions. The first one says 125 to the 1/3 power. So that's basically the same thing as the cube root of 125. Now, you could do that on your calculator by doing this, but let's just try and do it by hand. If I take 125 and I break it down into its prime factors, that would be 5 times 25, which is 5 times 5 times 5, or 5 cubed, right? So 125 to the 1/3 power is equal to 5 cubed to the 1/3 power, right? Because 120, in fact, let's do this. Let's see here. Let's change colors. Okay, so 125 is the same as 5 cubed. So 125 to the 1/3 power is the same as 5 cubed to the 1/3 power. Now, recall from a little while ago when we reviewed the properties that a power raised to a power, you would multiply the exponents. What is 3 times 1/3? It's 1. So the cube root of 125 is 5. Or I could say the cube root of a cube gives you the base. Why is this true? Because the cube root of 5 cubed would be 5 to the 3/3 power, which is 5 to the 1 power, which is 5. So when we switch this from radical form to exponential form, the exponent goes on top, the power does, the index goes on the bottom. 3/3 reduces down to 1, and 5 to the 1 power is just 5. So in a sense, the index and the exponent kind of reduce down to something to the 1 power. Now, do you have any questions about any of that stuff? I kind of threw a lot of different things at you here. This is another one of those sections where it's going to take you a while to chew on it and get it down correctly. Okay, what about this? -1000 to the 1/3 power. So that's like taking the cube root of -1000. First of all, can we take the cube root of a negative number? Absolutely. You can't take an even root of a negative number, okay? You can take an odd root. So the cube root of -1000 is going to be -10, because -10 times -10 times -10 is -1000. Okay. What about this one? 1/16 to the 1/2 power. Well, recall a quotient raised to a power, you attach the power to both the numerator and the denominator. 1 to the 1/2 power, that's taking the square root of 1, which is 1. What's the square root of 16? 4. Okay with that? Any questions on that example? Okay, how about this example? 1/16 to the -1/2 power. Well, the first thing I'm going to do is rewrite that as 16/1 to the +1/2 power. Taking the reciprocal of the base changes the sign of the exponent. But isn't 16/1 just the same as 16? So I've got the square root of 16, which is 4. How are we doing? Everybody still okay? All right, let's wander further into the deep end. Let's say I've got 4x to the 4th, all to the 1/2 power. The directions say this: simplify each expression. Assume that the variables can be any real number. Now they changed the directions on us. Yesterday they said, assume the variable is unrestricted, which is the same way as saying it can be any real number, but now they're saying it can be any real number, okay? And use absolute value symbols when necessary. Okay, now recall, when you take an even root of a number, you can't get a negative answer. We're taking the square root of all this because it's the 1/2 power. A product raised to a power, you attach the power to each factor inside. 4 to the 1/2 power is 2. A power raised to a power, you multiply the exponents. 4 times a half is 2, so we get x squared. Now, I took a square root, a second 1/2 power, so I have to make sure I don't have any negative answers. And recall that x can be any real number. However, x squared wouldn't be negative, so I don't need to use absolute value bars in this instance. Okay. How about this problem? Let's see here. X squared to the 1/2 power. Well, a power raised to a power, you would multiply the exponents. So you get x to the 2/2 power, which is x to the 1 power, which is x. But hold on, we're taking an even root, raising it to the 1/2 power. So the answer can't be negative, but they said the variables can be any real number. So in this case, we would have to take the absolute value, or apply the absolute value to the final answer. Okay. Let's see here. And again, if I'm going too fast, please let me know, stop me, say, hey, I need to write stuff down. I'm not in a hurry. I'm not going anywhere. There's no place to go. Okay. How about this one? -16 q to the 4th power, all raised to the 1/2 power. So again, we have a product raised to a power. So we're going to attach the outside exponent to each factor inside. So what would -16 to the 1/2 power equal? It's not real, because that's like taking the square root of a negative number. No can do. So it doesn't really matter what this is. If any part of it's not real, the whole thing's not real. Okay. Let's see here. How about this one? 243 x to the 10th power, all to the 1/5 power. So that would be 243 to the 1/5 power, x to the 10th to the 1/5 power. 243 to the 1/5 power. Well, I could do that on my calculator. 243 to the parentheses 1 divided by 5 power. And I get 3 x to the what? 10/5, which is x squared. Since x is being squared, I don't need an absolute value bar. Or if I don't want to use my calculator to do this, I could say, well, 243 is 3 times 81, which is 3 times 9 times 9, which is 3 times 3 times 3 times 3 times 3, which is 3 to the 5th power. So all of that could go in the place of that, and you'd have this. Okay, replacing 243 with 3 to the 5th. And this would be 3 to the 5th to the 1/5 times x to the 10th to the 1/5, which would be 3x squared. Now, my guess is you'd prefer to do it on the calculator, but I'm just pointing out that you could break it down into prime factors. And again, this 5 times 1/5 is 1. So taking the 5th root of something to the 5th power, you're going to get the something. There, the 5th root of something to the 5th power equals the something. Okay. Any questions? All right. How about this example? 27 to the 2/3 power. I could think of that as 27 squared to the 1/3 power, or 27 to the 1/3 power squared. Now, if I was going to do that on my calculator, 27 caret 2 divided by 3 equals, it wouldn't really matter. I do it all at once. But if I'm going to do it by hand, as I mentioned earlier, it's typically easier to do the root first. Because if I do this one, 27 squared, I can't do that in my head. I'm going to have to figure that out on a calculator or multiply it out. And then I got this huge number to take the cube root of. But I can take the cube root of 27, that's 3, and then 3 squared is 9. So by doing it this way, I can just do it in my head, so to speak. Any questions there? And again, if you're using your calculator, don't forget to quantify your fraction exponent. Okay, let's see here. Negative 125 to the 4/3 power. So I'm raising negative 125 to the 4th power, and I'm taking the cube root. Or I could take the cube root of negative 125 and then raise it to the 4th power. I think I would choose to do the root first and then the power. What's the cube root of negative 125? Well, negative 125 is negative 5 times negative 5 times negative 5. So that's going to be negative 5. And then raising that to the 4th power is going to be negative 5 times negative 5 times negative 5 times negative 5, which is 625. Okay. But here again, I could, on my calculator, I could put in parentheses, negative 125, close parentheses, little caret, 4 divided by 3. Make sure that you put the parentheses around the negative 125. Okay. It may not make a difference in some cases, but in some it does. So always a good idea to put it there just in case. Okay. Let's see here. We're going to go on. This says change each radical to an exponential expression. So the 7th root of 7p squared q would become 7p squared q all to the 1/7 power. Okay. So we're just changing it from one form to the other. We're not simplifying it or anything, just converting it from one form to the other. The square root of x squared plus y squared would be x squared plus y squared all to the 1/2 power. Let's go the other direction. Let's take some exponential expressions and write them as radicals. 6x cubed x cubed y to the 1/4 power would be the 4th root of 6x cubed y. X cubed plus y cubed, the quantity to the 1/3 power would be the cube root of the quantity x cubed plus y cubed. Okay. Questions there? All right, let's deal with some negative exponents. 4 to the negative 1/2 power would be 1/4 to the positive 1/2 power, which is 1/, the square root of 4, which is 2. 49 to the negative 1/2 power is 1/49 to the positive 1/2 power is 1/7. 8 to the negative 1/3 power is 1/8 to the positive 1/3 power is 1/2. Any questions there? Okay, negative the quantity 81 c to the fourth, all to the negative 3/2 power. Now, the negative 3/2 exponent is only attached to the parentheses. That negative sign out in front is not part of the exponent thing, okay? So this is going to become negative 1 over 81 c to the fourth to the positive 3/2 power. In fact, I'm going to do this. I'm going to move that negative sign right out there. Okay. And that's equal to negative 1 over 81 to the 3/2 power c to the fourth to the 3/2 power. These are the same kinds of problems you would have done back in beginning algebra in chapter 5. Only now the exponents are fractions, but it's the same rules. 81 to the 3/2 power. Let's take that and deal with it by itself. 81 to the 3/2 power. I could take the square root and then cube it, or I could cube it and then take the square root. I would choose to take the square root and then cube it because it's easier. What's the square root of 81? 9. So this is 9 cubed. Well, that's pretty big. Let's see here. 9 cubed is 729. So we've got 729. That came down here to be that. And then c to the fourth to the 3/2 power would be c to the 12/2 or c to the 6th power. So our final answer is negative 1 over 729 c to the 6th power. And you could write that with the negative sign out in front, or you could put it in the numerator, either way. Any questions about that problem?
Can you re-explain this C to me, please?
Sure. Okay. So from here.
Yeah.
All right. So we got it down here. Let's do this. All right. So we've got c to the 4th power to the 3/2 power. So we have a power raised to a power. So we multiply the exponents. 4 times 3/2 would be 12/2 or 6.
Okay, so you don't divide and then divide by 2 and then multiply by 3. You automatically just
well, you could do this. You could reduce that down to a 2 over 1, and then 2 times 3 is 6.
Okay.
Yeah. So yeah, you could do that. All right. Okay. We good to go on? All right, let's take a look at one more of those. 25 over 49, all to the negative 3/2 power. So the first thing we're going to do is take the reciprocal of the base, which makes the exponent change sign. So now it's a positive 3/2. We have a quotient raised to a power, so we're going to attach the outside power to both the numerator and the denominator of the quotient. I need to take 49 and I need to cube it, and I need to take the square root. I'm going to take the square root first and then cube it, and I'm going to do the same thing in the denominator. Take the square root and then cube it. So what I'm doing now, instead of taking the two exponents and multiplying them together, I'm pulling them apart. Instead of saying, well, 1/2 times 3 is 3/2, I'm saying 3/2 could be written as 1/2 times 3. So this becomes that, and this becomes that. I'm breaking apart the power and the root because I'm going to do them separately. and I want to do the root first because it's easier. So now what is 49 to the 1/2 power? That's 7. So that's going to end up being cubed. And 25 to the 1/2 power, that's 5. So that's going to end up being cubed. Then we get what? 343 over 125. You okay with that? All right. Now, let's take a look at this situation. 9 to the 3/7 power times 9 to the 2/7 power. We're multiplying two powers with the same base. So we add the exponent. So this is 9 to the 3/7 plus 2/7, which is 9 to the 5/7 power. Four to the 2/3 power times 4 to the, oops, my bad. 4 to the 2/5 power times 4 to the 2/5 power would be 4 to the 2/5 plus 2/5 power, which is 4 to the 4/5 power. Okay. 6 to the negative 2/3 power times 6 to the negative 4/3 power would be 6 to the negative 2/3 plus negative 4/3, which is 6 to the negative 6/3 power, which is 6 to the negative 2 power, which is 1 over 6 to the positive 2 power, which is 1 over 36. Oh, yeah. Bring your lunch with you when you do these problems. So what am I doing? I'm adding the exponents. I reduced it down and then, oh, it was a negative exponent. So I rewrite it with a positive exponent and then I applied the exponent to get the 1 over 36. Any questions on this one? Nope. Okay. B to the 3/5 power times B to the 2/5 power, the whole thing raised to the 8th power. So inside the parentheses, I'm multiplying two powers with the same base. So I'm going to add the exponents. But 3/5 from 2/5, or excuse me, 3/5 plus 2/5 is B to the 5/5, which is B to the 1, which is just B. Oops. But that whole thing is to the 8th power, so we've got B to the 8th power. So basically, inside reduced down to just B, because 3/5 plus 2/5 is 5/5, which reduces to 1, and B to the 1 power is just B, and so all of that. So simplifying it all inside, we get B and then to the 8th power. All right, how about this one? Y to the 2/5 power times y to the negative 2/5 plus y to the 3/5. Distributing, I get y to the 2/5 times y to the negative 2/5 plus y to the 2/5 times y to the 3/5. Okay, so what are we doing here? We're multiplying two powers with the same base. So we add the exponents. What's 2/5 plus -2/5? That would be y to the 0 power. But what's anything other than 0 to the 0 power? It's 1. And y to the 2/5 times y to the 3/5 would be y to the 5/5, which is y to the 1, which is just y. So final answer, 1 plus y. Okay. What about this one? The 6th root of 7 cubed. It says, use rational exponents to simplify each radical. Okay, so this may seem crazy, but initially this is what we're going to do. We're going to take this radical, we're going to rewrite it as an exponential expression, then we're going to simplify the exponential expression, and then we're going to rewrite it back as a radical. And eventually you'll see what's going on and you can skip the middle step. But this is the same thing as 7 to the 3/6 power, right? I think I did it right this time, finally. Which would be 7 to the 1/2 power, which would be the square root of 7. Isn't 6 divided by 3, 2? Just saying. And that's kind of eventually where we'll get to. All right. Let's see. The 12th root of 13 to the 4th power. So that would be 13 to the 4th power. Oh, excuse me, 4/12 power, which would be 13 to the 1/3 power, which would be the cube root of 13. So again, we're just taking 12 divided by 4 equals 3. But we're doing it this way to kind of get you used to how it works. How about this one? The 6th root of x squared y squared. So that would be x squared y squared to the 1/6 power, which would be x squared to the 1/6 power, y squared to the 1/6 power, which would be x to the 1/3 power, y to the 1/3 power, which would be xy to the 1/3 power, which would be the cube root of xy. Now I know I kind of zipped through that at 100 miles an hour. So I'm taking this and changing it to a 1/6 exponent. Then I'm applying it to each factor. A power raised to a power, you'd multiply the exponents. And then I just kind of went backwards and said, well, if each one's to the 1/3 power, the whole thing's to the 1/3 power. So therefore it's the cube root. Okay. How about this one? The 4th root of the square root of x. Well, that would be the square root of x to the 1/4 power, which would be x to the 1/2 power to the 1/4 power, which would be x to the 1/8 power, or the 8th root of x. Now, again, what am I doing? I changed that into an exponent. I didn't do anything with that yet. Then I took this and said, well, the square root's the same thing as the 1/2 power. A power raised to a power, you multiply the exponents. 1/2 times 1/4 is 1/8. So that's where I got that, but that's the same thing as the 8th root. Okay. All right. How about this one? 2 to the 5/6 power times 2 to the 1/3 power over 2 to the 1/2 power. So in the numerator, we're multiplying two powers with the same base. So we're going to add the exponent. So this is 2 raised to the 5/6 plus 1/3 power. Okay. But now I've got two fractions as part of the exponent, 5/6 plus 1/3. To add those, I need a common denominator of a 6. So I'm going to multiply 1/3 by 2 over 2. So 5/6 plus 1/3 becomes 5/6 plus 2/6, which is 7/6. So now my numerator is that. And then the denominator we haven't done anything with yet. Now we're dividing two powers with the same base. So we've got the base with the top exponent minus the bottom exponent. Well, 7/6 minus 1/2, common denominator is a 6. So 7/6 doesn't change. The 1/2 we multiply by 3 over 3. So we get 7/6 minus 3/6, which is 4/6, which reduces down to 2/3. So we end up with 2 to the 2/3 power. There, we just reviewed everything you learned in Math 50, Math 75, and Math 85 in one problem. It seems like. Well, I think I've tormented you enough today, don't you? Think you've had enough torture for maybe for like the next 3 weeks or something. But anyway, I will be back this afternoon at 1:15 with an office hour. And I'm going to go ahead and stop the recording.